Hi. In this video, we're going to talk about derivatives. And we're going to begin with a graphical understanding of what a derivative is. So we're going to start with a circle. And if you think back to geometry, when you have a circle, if you draw a line that connects 2 points on the circle and continues to go through them, not just connect them, we call this line a secant line. And if you have a line that goes through one and only one point on the circle, let's say the point here, we call this a tangent line. Now, in calculus, we take this concept of tangents and secants, and we'll look at a curve. So let's say we have a curve, a regular parabola, and let's say I have a point here, P. I can draw a secant line that joins P and some other point. Let's call it Q. And the line that goes through both P and Q would be a secant line. Now, how would you find the slope of that line? Remember back when you do slope, this P has an x value and a y value, and this Q has an x value and a y value. So I'm calling them x1, y1, x2, y2. And you'd find the slope, and there you go. Now what if I kept moving that Q such that it got closer and closer and closer to P? That eventually the line that I'm trying to connect between P and Q eventually be is just P and P. Because what if I move that Q right on top of P? So again, if I draw this in red so you see a little bit more, if I kept moving this Q closer and closer and closer to P, that eventually I'm just looking at the slope of the line at P. At P, because now P and Q are actually right on top of each other. Now imagine that. If P and Q are both this, if I were to put that in the slope formula, it's going to get 0 over 0, right? Because it's like the same point minus the same point. And remember what the slope formula is? y2 minus y1 over x2 minus x1. So again, just to remember what I was saying before, if you wanted to find the slope of that secant line, you would have taken x2 and the y2 and the x1 and the y1 and substituted into the slope formula. That's how you find the slope of the secant line. However, we want to know what's the slope of the tangent line at a point. I'm going to write that down. Slope of the tangent line at the point P, which is x1, y1. And if P is really Q, so say to the 4, to up sub 4, you plug that in and you're going to be like, okay, it's the same point, so I'm going to get 0 over 0. But what's nice is that you can realize that the slope at a point P is actually the slope of the tangent line at that point, which is really one of the main ideas here of differential calculus. So let's continue with the idea that was just mentioned. You have a curve, you have a point P and Q. Now let's just relabel the x and y values of the points P and Q. So let's P is the point A, comma f of A. And Q is the point Z, comma f of Z. Remember, that's just function notation. F of the x value gives you the y value. So the Q point is Z, comma f of Z. I want the slope of the line between them. So let's say I draw a line that connects P and Q. I want to know the slope of that line. So M is equal to y2 minus y1 all over x2 minus x1. So let's substitute in the values. F of Z minus f of a all over z minus a. Now, what if we were to take this distance between a and z and make it smaller and smaller and smaller, just like I was saying in the previous segment? If you keep putting different values of q here, and you bring it closer and closer, the distance between p and that q smaller and smaller and smaller. Same here, the distance between a to z getting smaller and smaller and smaller. Well, let's call this distance here h. The distance being z minus a. And if we keep making this distance getting smaller and smaller and smaller, what value am I making h getting close to? It's getting smaller, smaller, and smaller. And eventually till they're the same point. What would their distance be? 0. So what you want to do is you want h to go to 0. So if you put that in front of this statement, h goes to 0. And remember, we just looked at limits, right? And the limit means what happens is the curve gets really close to a value, but not at the value. Because remember, if h was equal to 0, and you did f of a minus f of a all over a minus a, you get 0 over 0, and that's undefined. But we don't want the value. We want to know what is the limit. What is it getting really close to when h goes to 0? Now, h is not a point on the curve, but a distance between 2 points. So we're going to look at the limit as h approaches 0 of the slope between 2 points. So what we want to do is we want to make the secant turn into a tangent. So this is one basic idea of what we want to do to find the slope of a tangent line at a point. Now, if I take a look right here at this, h is equal to z plus a. So if h is equal to, z minus a, add the a to the other side. H plus a is z. Let me write that as a plus h is z. And then I'm going to come up here and I'm going to rewrite this idea. And then I'm going to rewrite this idea. So I'm going to say, okay, well then this is equal to f of, what's z? A plus h minus f of a all over a plus h minus a. And I'm just going to do that really quick here. A plus h minus a, h. So I'm going to do that same thing here, because this is the key idea. This limit, as h approaches 0, of f of a plus h minus f of a all over z minus a, or in this case, not z minus a, h is equal to the slope of the tangent line at a point. At a being the point.